Consider the following question. A four-sided die is rolled and then re-rolled that many times it came up on the first roll. And y then is the sum of all these rolls, including the first one. Then we are asked what are A, the probability that y is equal to 5, and B, the expected value of y. So a four-sided die can produce values from 1 to 4, which means depending on the first roll we could have up to 5 rolls total. The rolls would be assumed independent because nothing else is said. So let's call the value of the ith roll, which is in the 1 to 4 range, xi. And then by total probability, we can evaluate the probability that y is equal to 5. In particular, the probability that y is equal to 5 is going to be the total probability expanded over how many rolls we have, i.e. what the value of x1 is. In particular, it's the sum from j is equal to 1 to 4 of the probability that y is equal to 5 given x1 is equal to j times the probability that x1 is equal to j, i.e. j more rolls. And then we can just expand out because of the possibilities. So given that x1 is equal to 1, we have one additional roll. And so that would mean the second roll would have to be 4 in order to produce a sum of 5. So we have the probability that x2 is equal to 4 conditioned on x1 is equal to 1 times the probability that x1 is equal to 1. Next, if x1 was equal to 2, then we'd need the sum of x2 plus x3, the second and third roll, to be equal to 3, because we'd have 2 plus the other 3 is equal to 5, i.e. the roll on the first outcome has to be 2, and then the next 2 has to be 3. So we'd have the probability that x2 plus x3 is equal to 3, given x1 is equal to 2, times the probability x1 is equal to 2. Now all the rolls are independent, so the probability that x2 is equal to 4 given x1 is equal to 1 is just the probability that x2 is equal to 4. And similarly, the probability that x2 plus x3 is equal to 3 given x1 is equal to 2 is just the probability that x2 plus x3 is equal to 3. And now we can then just evaluate them. So the probability that x2 is equal to 4 is a quarter. The probability that x1 is equal to 1 is a quarter. The probability that x2 plus x3 is equal to 3 is the probability that x2 is equal to 1 and x3 is equal to 2, or vice versa, x2 is equal to 2 and x3 is equal to 1. Each of those is going to have a value of 1 over 4 squared, which is equal to 1/16, so the sum of that will be 1/8. And all the other probabilities there must be a quarter. So we wind up with a quarter times a quarter plus an eighth times a quarter, which is equal to 3 over 32. For part B, we use indicator functions in lieu of conditioning. And so if we think of y, well, x1 would always count in y. And x2 also would always count in y. And we could write that as x2 times the indicator that x1 is at least 1, which it always is. Now x3 would count in y if and only if x1 were at least 2, i.e. it indicated 2 more rolls. So we would add on x3 times the indicator that x1 is greater than or equal to 2. Likewise, x4 counts when x1 is at least 3, and we write that as x4 times the indicator x1 is at least 3, and then we add on x5 in the last case when x1 is at least 4. So we have this expression y is equal to x1 plus x2 times an indicator plus x3 times an indicator plus x4 times an indicator plus x5 times the indicator that x1 is at least 4. So we had 4 extra rolls, a total of 5 rolls. And now we just could write out the expectation. So the expectation of y is the expectation of x1 plus the sum of these xj's, j is 2 to 5, times the indicator that x1 is at least that j. by making j run from 1 to 4, we could write that y is equal to x1 plus the summation of j is 1 to 4 of xj plus 1 times the indicator that x1 is at least j. So at least j more rolls to have the j plus first roll count. Then what we can do is we can use total expectation. So rather than just leaving that as an expectation, we can use total expectation to write it as the expectation of a conditional expectation, conditioning on the random variable x1, the number of extra rolls. And then we can use linearity to divide up the conditional expectation. So we could write the conditional expectation as the expected value of x1 given x1 plus the summation j equals 1 to 4 of xj plus 1 times the indicator that x1 is at least j conditioned on x1, and then take the expectation outside of all of that. Well, by taking out what is known, when you're taking the expected value of x1 given you know x1, of course that's just x1. And that means we can also bring out the indicator function. So we can bring out the indicator functions for each j. So we'd have the summation j equals 1 to 4 of the indicator that x1 is greater than or equal to j times the expectation of xj plus 1 given x1. So we brought out something that's a function of x1 when we're conditioning on x1. So it's known when we can bring that out. And now we just use the linearity of the expectation, and so we have that the expectation of x1 plus the sum j equals 1 to 4 of the indicators times the conditional expectations is the expectation of x1 plus the expectation of the sum j going 1, but now we stop j at x1, right? Because that indicator function, all that does is it says don't sum past x1. So that's the same as summing from 1 up to x1, and then we just repeat the conditional expectation inside of xj plus 1 given x1. And then we take the expectation of all that stuff. And now by independence, we know that the expectation of xj plus 1, j is at least 1, given x1 is the same as the expectation of xj plus 1, and that's 2.5. The expectation of x1 is also 2.5 because it's a four-sided die. It's easy to sum up the sides and then divide by all four possibilities, and you get 10 over 4, which is 2.5. Therefore, the expectation of y is equal to the expectation of x1 plus 2.5 times the expectation of the sum of 1. So you sum from j equals 1 up to x1 of 1. And that's just the expected value of x1. So we wind up with 1 plus 2.5 times the expected value of x1. 1 plus 2.5 is 3.5. As we mentioned, the expected value of x1 is 2.5. So we wind up with 3.5 times 2.5, which is 8.75.